All right, so the data set we'll look at now, and you see in the table below, represents a random sample of 150 cases of mothers and their newborns in North Carolina over a year. 4 cases from the data set you'll see are represented here. The value NA, by the way, shows that the first 2 entries of the first variable are missing, so we don't know what that data are. A particular interest for us is the 2 variables that are highlighted, weight and smoke. So the weight of the baby, newborn baby, and whether or not the mother smoked during pregnancy. So we would like to know if there's convincing evidence that newborns from mothers who smoke have a different average birth weight than newborns from mothers who do not smoke. So we'll use the North Carolina sample to try to answer that question. And you see, here's the histogram that represents both birth weights for infants mothers who smoke and not smoke. The top one is for the mothers who did not smoke. The bottom one is for mothers who did smoke. And you can see that both exhibit some strong skewness. That most babies are around a certain weight. There's only a few that are very small, at least relatively speaking. Anyway, as far as the conditions go, independence, we were told this is a random sample, so yes, we have independence. Normality, both distributions show some skewness, but the sample sizes are at least 50. One is 100, the other is 50. The central limit theorem guarantees normality because, again, the larger the sample size, the less the skewness matters. And once we're around 50 or so, we can get by with a lot of skewness. The point estimate is the difference of the 2 means, which you see at the top of the table, 7.18 minus 6.78. So there's a 0.4 pound difference between the 2 babies. Standard error, you can calculate yourself. It's the square root of 1.6 squared over 100 plus the 1.43 squared over 50. It comes out to be 0.258. The test statistic is the point estimate minus 0 divided by the standard error, so essentially 0.4 divided by 0.258. That comes out to be a test statistic of 1.55. Degrees of freedom, well, the smaller sample size is 50, so we'll use 50 minus 1 or 49 degrees of freedom. And then the p-value, again, we go second, bars, choose the TCDF. Test statistic was 1.55. 999. 49 degrees of freedom. Paste. Times 2. So, p-value 0.128. That's more than 5%, so we should fail to reject the null hypothesis. Essentially, there is no evidence that the weights of the babies born to mothers who smoke or don't smoke are different. So, given our conclusion, could we have made a type 1 or type 2 error? Well, a type 1 error is when you should fail to reject, but you rejected mistakenly. A type 2 error is when you should have rejected, but you failed to reject. So, if we did make an error, it's going to be a type 2 error. And that we did fail to reject. So if it was wrong, we should have rejected. That's a type 2 error. And if I want to reduce that, well, again, it is possible we've committed a type 2 error and that there really is a difference between the weights of mothers who, the babies born to mothers who smoke and don't smoke. If you want to reduce the possibility of this error, well, just try larger sample sizes. So to reduce the possibility of this error, use larger samples. The standard error will decrease, and the p-values will shrink. Another thing you could do is increase the level of significance, say like 0.1. Make it easier to reject.